Section 9.4 talks about the rate of effusion of a gas, which is also called Graham's law. So the difference between diffusion and effusion, we often talk about diffusion of gases because gases can spread out in the air of a room. So if you have something with an odor, some perfume, or some food on one side of a room, eventually that smell will reach all the corners of the room. And that is called diffusion. Something that is easier to measure, which is how Graham came up with his mathematical relationships, is effusion, which is a small opening, having gas molecules escape through a small opening. And so that is easier to measure. They are similar rates though. What happens is that both of these processes, diffusion and effusion, take place more quickly for smaller gas particles with a smaller molar mass. And the proportionality is that the rate of effusion is proportional to 1 over the square root of the molar mass. So it is pretty interesting in the outside video, I think there's more than one, that shows two gases diffusing through a tube. And the gases picked are hydrochloric acid and ammonia because when they come together, you can see a cloud of tiny solid particles forming, the solid ammonium chloride particles. And so you can see exactly where the gases meet, and they don't meet in the middle because they have different molar masses. So that is pretty interesting. I encourage you to check those videos out. So the result of this is that if you have a gas that you don't know the molar mass of, you can compare its rate of effusion to a known gas and figure out what the molar mass of the unknown gas could be. Since the rate of effusion is inversely proportional to the square root of the molar mass, comparing two rates, A to B, is going to have these kind of flipped because A is proportional to 1 over the square root of the molar mass of A, and B is proportional to 1 over the square root of the molar mass of B. Let's say that we have a case where A is a smaller gas. Then that means that this is going to be smaller and this is going to be larger, and so the square root of the larger number over the square root of the smaller number is going to give you a result that is greater than 1. And so the smaller gas is going to be more than 1 time as fast as the larger gas. So it's going to be a larger rate than the rate of the larger gas, which will have a slower rate. So we'll have a faster rate over a slower rate. So the effusion of the smaller gas is going to be faster. And then if A were a larger gas, we'd have the opposite. We'd have it having a slower rate of effusion. Let's have the same situation where we propose A being smaller. Again, A doesn't always have to be smaller. I'm just trying to take a look. If A is smaller, what does this do to the comparison of the rates? What does this do to the comparison of the time? So you'll notice that this time we don't have them flipped. Last time B was on the bottom and the square root of the molar mass of B was on the top. Now we have both B and the square root of the molar mass of B on the top. So we still have the smaller number on the bottom, which gives us a number that is greater than 1. And that means that the time it takes for B to effuse is more than 1 times the time that A should effuse. So the time for B is larger than the time for A, so that the time B over time A gives a number greater than 1. So what we have is that the time that it takes for B is going to be larger than the time it takes for A. So if A is a smaller gas, the rate of effusion is going to be larger than the rate of the larger gas, but the time it takes is going to be smaller than the time of B. And that makes perfect sense. If you do something faster, you're going to take less time to do it. So these are the reverse of each other. The rate of the smaller gas is going to be larger. The time it takes for the smaller gas is going to be smaller. All right, let's try this with an example. We have one known gas that is carbon dioxide. Let's call this B. And we know the molar mass of B, we can add it up from the periodic table. It is 44.01 grams per mole. And what we are looking for is the molar mass of A. What else do we know? We know that the rate of this unknown gas A is 1.25 times the rate of B, or the rate of carbon dioxide. Let's use that. And that means that the rate of A over the rate of carbon dioxide is 1.25. So A diffuses faster. If we divide that rate by the rate of CO2, we get a number larger than 1. We get 1.25. From Graham's law, we know that the rate of A over the rate of carbon dioxide is the square root of the mass, the molar mass of carbon dioxide, divided by the square root of the molar mass of the unknown gas A that we are trying to find. And we know from here that that rate, A to CO2, equals 1.25. So if we rearrange this equation, we get that the square root of the molar mass of CO2 is the square root of the molar mass of A times 1.25. Let's go ahead and put this in here. The square root of 44.01 grams per mole over 1.25 equals the square root of the molar mass of A. And then if we square both sides, we will get the molar mass of A. So let's square this side, and we'll square that side. Okay, so when we take the square root of the 44.01, we get 6.634. I just kept grams per mole under the square root sign because I don't know how to take the square root of grams per mole. And then this is over 1.25. And then if we square this, that is this term over here, that is going to be the square root of the molar mass of A squared, which is the molar mass of A. So I've just sort of rearranged this equation here. And then when I divide 6.634 by 1.25, I get 5.307. And then when I square that, I get 28.17 grams per mole. And it's not surprising that this is a smaller number than 44.01 because it has a higher rate of effusion. So when we were told that the rate was 1.25 times the rate of carbon dioxide, then we could have made a prediction that it would be a smaller gas since it travels faster. Okay, so this next problem has to do with the time that it takes. So first let's make a prediction. So we have nitrogen gas that takes 436 seconds to effuse through a membrane, and we want to compare helium. Helium is a smaller gas than nitrogen, and so we think it should take less time. So I'm going to make that prediction. So I'm just putting helium as gas A and nitrogen as gas B. This will still work if you had them swapped. I just have to pick one way and go with it. And so the time for helium over the time for nitrogen is proportional to the square root of the molar mass of helium over the square root of the molar mass of nitrogen. And so we know 3 out of these 4 terms, we can put them in and solve for the time for helium. So it's up to you if you want to plug in the numbers first or if you want to rearrange it algebraically first. If we rearrange it first, we're going to take the square root of the molar mass of helium, divide it by the square root of the molar mass of nitrogen, and then multiply that result by the time it takes nitrogen. So let's go ahead and put in numbers now. We have the molar mass of helium, the molar mass of nitrogen, and the time for nitrogen. We can probably see that this is going to come out to a number less than 1, which is going to make this a smaller number than 436. So when I do this, I get that it is 0.3780 times the 436 seconds, which is 165 seconds. So it is a faster time for the smaller gas to get through the membrane.